So one of the most basic skills that you need for organic chemistry is being able to draw Lewis structures and to be able to calculate formal charge for those structures. So what we're going to do is a little bit of Lewis structure drawing 101, just to do a refresher, and then we'll do a little bit more complicated structures as we go on. So let's go ahead and try to draw one of the more simple molecules that we could ever draw, which is water. So water has the structure of H2O, and right now I want you to try to go ahead and pause the video and try to draw the Lewis structure for water. Okay, so if you were to draw the Lewis structure, you probably would have drawn it something like this. So you've got your oxygen, and you've got your hydrogen, and your hydrogen. And then after that, you may be filling in covalent bonds like this. And there's nothing necessarily wrong with that, but we're going to try to do this a different way. So instead of drawing the Lewis structure for water like this, with all of the covalent bonds drawn out as electron pairs, we're going to try to employ a different method for the rest of the organic chemistry curriculum, which is we're going to do our drawings using a slightly different method. And the formal way of talking about this method is these are not Lewis structures, they're what are called Kekulé structures. So probably you've been drawing Kekulé structures and not even knowing it, but the only real difference between the Lewis and the Kekulé structures is that instead of drawing those electrons right here as electron pairs, we're going to draw them as a single line. So this line right here is telling your viewer, or the person who's reading your structures, that there are two electrons within that bond. So the way we would draw the formal Kekulé is to draw those two bonds, and then we would include the lone pairs of the electrons for the water. Okay, so from now on, try to get used to this method, and I'll probably use the term Lewis and Kekulé kind of interchangeably to actually notate that I really want you to draw them like this. Okay, so whenever I'm drawing these structures, I usually go through a little mental checklist in my head. So that checklist looks something like this. So this is my checklist, and there are 3 parts to my checklist. The first thing that I want to do is to make sure I'm not violating a very, very fundamental rule for drawing Kekulé structures or Lewis structures, which is called the octet rule. So hopefully you've heard of the octet rule at least one time, and if not, we'll just kind of go over the octet rule very quickly. So the octet rule says that for some atoms, and specifically a lot of the atoms that the elements that we're going to be dealing with in organic chemistry, the most number of electrons that can be surrounding that atom will be 8 total electrons. So if you look at this oxygen right here, we've got 2, 4, 6, 8 total electrons for that oxygen. So we have satisfied the octet rule for that oxygen. If, on the other hand, we had drawn one other pair of electrons for that oxygen, we would have violated the octet rule, because now if you count the total electrons that are surrounding this oxygen, we have 2, 4, 6, 8, 10. So this is a violation of the octet rule. So this is a very fundamental rule that you always want to try to double check. Okay, so it looks like we haven't violated the octet rule for my oxygen, and we'll talk about some of the atoms that we need to really worry about that are subject to the octet rule. Okay, so other than the octet rule, there's another little subset of that rule called the duet rule. So the duet rule is very specific. It only deals with hydrogen. So this particular hydrogen, for this particular hydrogen, we need to make sure that we never have more than 2 total electrons surrounding that hydrogen. So right now, within this bond, there are 2 electrons. So we've formally satisfied the duet rule for this hydrogen. If, on the other hand, we had drawn a lone pair on this hydrogen, we would have violated the duet rule, because in that case we would have had 2 and then 4 total electrons that were surrounding that hydrogen. Okay, so if we had drawn the hydrogen this way, we would have violated the duet rule. Very important rule. Okay, so the second rule that is going to be very helpful is to always remember the valence for each of the atoms that we're going to be working with. So for oxygen, oxygen has 6 valence electrons surrounding it, And for hydrogen, hydrogen has one valence electron surrounding it. So whenever you write down the number of atoms that you're going to be using, you always want to try to make that summation of electrons equal the total number of electrons for each one of our atoms. So since we have only one oxygen, we would have had 6 electrons for that one oxygen, and then we have 2 hydrogens, so we would add 2 to that. So we get a total of 8, so we should have a total of 8 electrons here. So if we count 2, 4, 6, 8, we've satisfied our total valence electron count. So we're good on that. And finally, our third thing that we want to always double check is very, very important. It'll never go away. It's always a stumbling block for organic chem students, and that's going to be our charge calculation. So charge calculation. And we're going to do an example for this water molecule just to make sure that we're all comfortable with charge calculation. So the way that you calculate formal charge, there are a couple different ways that you could present this formula, but I find this way very, very simple. So formal charge calculation. If we wanted to calculate the formal charge for, let's say, the oxygen, we'll do that. And let's also do a formal charge calculation for the hydrogen. But if we want to do a very generic way of calculating formal charge, the way you would do this is you would think about the valence for that particular atom. Okay, so we want to think about the valence for each one of these atoms, and for oxygen it's going to be 6. So we're going to have 6 for oxygen, and we're going to have 1 for hydrogen. Then we're going to subtract the total number of covalent bonds. So we're going to take the covalent bonds, okay, covalent bonds, and we're going to subtract that. So if you think about the oxygen, if you look up here, this oxygen has 2 covalent bonds, so we're going to subtract 2 from that. And for the hydrogen, this one particular hydrogen has 1 covalent bond, so we're going to subtract 1 from that. And then the final step is to subtract the total electrons that act as lone pairs. So right now, if you look up at the oxygen for the water, this oxygen has 1, 2, 3, 4 total electrons that are in a lone pair configuration. So we're going to subtract 4 from this oxygen. And if you look at the hydrogen, we don't have any lone pairs for the hydrogen, so we're going to subtract 0 for that hydrogen. And not very surprisingly, we're going to get 0 as our formal charges. So 6 minus 2 is going to be 4, and then we subtract 4 from that, and we're going to get 0 for a formal charge for oxygen. And the formal charge for the hydrogen is going to be 1 minus 1, so 0. Okay, so not too exciting, but it seems to work out with the way that we've drawn our Kekulé or Lewis structure. If we had calculated that we needed a charge, we should have shown that charge. But the way we've drawn it, we're already kind of saying, okay, there's no charge there. Okay, so one final thing, these are very important valences for you guys to remember. These are going to be very prevalent for the remainder of this semester as well as next semester. So these are very good numbers to make sure that you do memorize. I don't advocate memorizing a whole bunch of stuff, but these are going to be very important. And so for hydrogen, like we've already said, hydrogen has 1 valence electron, so you need to remember that. Sometimes we'll see boron, so boron isn't as prevalent as a lot of these other atoms, but if we ever come across boron, you need to remember that boron has 3 valence electrons. Then carbon's going to be super duper important. We're going to see that a whole bunch. Carbon has 4 valence, and then nitrogen, we have 5 valence, and then oxygen, we have 6 valence, like we already said before, and then finally, fluorine, we're going to have 7 valence. Okay, and these are going to be the same for all of our halogens. So fluorine, chlorine, bromine, iodine, they're all going to have a valence of 7.